Hello students. So we've been using the generalized binomial theorem over and over again. We haven't proven it. So let's do that. Okay. So first of all, important point. We defined this. We define for any real numbers that are not whole positive integers, we define this to be, we go down and we go down and we keep going until we get to this. That was our definition. There's nothing to prove. We can't prove that because we just said it. We just said, okay, we're going to use this symbol to mean this. So that's not part of the proof. What is it that we want to prove? Well, we want to prove this, that 1 plus x to the alpha is equal to alpha, choose r, from this to this, x to the r. That's what we wish to prove. Okay. So how are we going to do this? Well, we're going to use Taylor series, the formula for Taylor series from Calculus 2. But first, let's start off by taking the derivatives of this. And there's a result. So it is that 1 plus x to the n, if I take the kth derivative of this, this is equal to n choose k factorial 1 plus x to the n minus k. So this is what we're going to prove first. And then we should be able to use Taylor series on this and hopefully see that that's what we get. Okay. So let's try that. Let's try to prove this. How might we do this? Well, let's start with induction. What are we going to do induction? We'll do induction on k. So what do I mean by that? Well, I mean we're going to show it works for k equals 0, regardless of what our n is at the time. And then we'll, you know what, I like using alpha here. Let's use alpha. Just more of an emphasis, because n's usually an integer. Okay, we're gonna show that it works for on k equals 0, regardless of alpha. And then we'll show that if it works for k, it works for k plus 1. Okay, so what's the case where we have 0? So that means we're taking the 0th derivative here. We're not taking the derivative at all. So when k equals 0, on the left-hand side, I'm just going to get 1 plus x to the alpha. And on the right-hand side, remember k equals 0, so I'm going to get alpha choose 0, which is just going to be 1. I'll talk about that in a second. 0 factorial. And now I get 0 for k, so that's just alpha. Now, we didn't explicitly state it, but what happens if we plug a 0 in here? Well, if we plug a 1 in here, we'll only have one term. If we plug a 0, we'll have no terms. But just like when you're adding and you're adding no terms, the standard thing is the identity, which is 0. Well, the standard thing to take for the 0 when you have the product of no terms is 1. So we get 1 over 0 factorial, 1 over 1, and that's why this is 1, and this is 1, and we get just this. So we have shown our basis case. Okay. So next, what do we want to do? Well, we want to assume, let's assume it's true for k. Well, not much point in me copying this, but okay, give us a chance to breathe. Take a deep breath. Okay, so we're assuming this, and we want to show that if we have one more derivative here, we'll get this. K plus 1 factorial, 1 plus x to the alpha minus k plus 1. Okay, so that's what we want to show. Okay, well, I know that this is just this with one more derivative. So what I'm going to do is I'm going to take this and take the derivative one more time. So I get this 1 plus x to the alpha minus k prime. And that's this left-hand side. So the left-hand side equals this. Okay, and I want to show it, I want to get to there. Okay, well I have to take the derivative of this, and keep in mind that this is a constant. Whatever number this is, I can just pull that out. So I'm going to pull out this, and now I'm going to take the derivative of this, okay, which is going to be what? Well, my exponent is alpha minus k, so I'm going to get alpha minus k, and this is going to be 1 plus x to the alpha minus k minus 1. Okay, so what do I have here? Well, let's see. I have an alpha k, k factorial, and an alpha minus k. Well, I know what alpha choose k is. This is this all the way to alpha minus k plus 1 over k factorial. But now I have this k factorial alpha minus k. Times this, which I can write like that. Aha, it's already matching over there. Okay, so now I'm just going to move this up there. And notice I have a k factorial over k factorial. I could cancel that because it's 1, but instead I'm going to make it k plus 1 factorial, k plus 1 factorial, because that's what I need. I can see what I'm trying to get at. Okay, so what's this going to be? Well, this is going to be all the way down to alpha minus k. Well, I'll write I don't know how many terms is best to write here, but you know what? I'll just write both of these two, alpha minus k. So I have one further term down here, and I have this. So what is this equal to? Oh, and let's finish writing this line before I ask such questions. Okay, what is this equal to? Well, how many terms do I have in the top? I have one more than before. This is going to be an alpha, choose k plus 1 now, because I have the k plus 1 factorial, and I have k plus 1 total terms in the top where I had k before. And now what do I have? I have a k plus 1 factorial and a 1 plus x alpha minus k plus 1 in parentheses. And that's exactly what I wanted to get. Right here, this matches perfectly. So that's our induction proof. Okay, so what did we show so far? We've shown this. So now, let's use Taylor series. And we're going to use Taylor series on this. So we're going to let f of x be 1 plus x to the alpha. And I'm going to apply Taylor series. So what does this tell me? Well, Taylor series says that f of x is equal to the sum of all the possible k's, where we take the derivative and plug in 0, the case derivative and plug in 0, we divide by k and take x to the k. Okay, so what do we get? We get that this is equal to. Okay, now I know what the case derivative is because we computed that. It's this thing. And what happens if I plug in 0 here for x? Well, I'm just going to get 1. I'm just going to get this thing here. So I'm going to get alpha, choose k, times k factorial. And now this is that. And then look what happened. I am done. So that is a proof of this statement right here, and the proof of the generalized binomial theorem.